Hello everybody, welcome into another lesson. So today we are going to talk about finding the slope of a curve at a point as well as the equation of a tangent line at that point. So up until now, all through algebra and all the way through pre-calc and up until this point, you've been dealing with the slope of a line, which has a constant rate of change. No matter where you're at on a line, the slope is the same everywhere. A name for a slope, of course, is a rate of change. If you think about it, a slope is change in y over change in x. Well, that's a rate of change, the rate of the change in y to the change in x. And another name, which we're not really going to deal with right now, another name for that slope or rate of change is the derivative. We're not really introducing derivatives today, but I just want you to be familiar with that name because that's what a derivative is. But we're going to deal with slope and rate of change today. So, as I said, in algebra, all the way up until now, you've been dealing with a constant rate of change on a line. Well, here we have the graph of f of x equals x cubed, the standard graph of f of x equals x cubed. You can clearly see that if you go to different points on the curve, you're going to have different slopes. The idea of calculus is to be able to figure out variable rates of change. That's where calculus comes in, is to deal with variable rates of change and not the same rates of change. So that in general is what the goal of calculus is for the derivative side and finding slopes and tangent lines. Now, you may be familiar with the term tangent line all the way back to geometry, especially when we talked about circles. There's that theorem that says that the tangent line to a circle is perpendicular to the radius at its point of tangency. And that's true. However, when you get into trying to find the tangent line to curves, that's where basic geometry is not sufficient, and that's where calculus comes into play. You have to use calculus to do that. So let's talk about, in general then, a secant line and a tangent line. So I'm going to draw a secant line in blue. If we recall from geometry, a secant line connects 2 points on the curve. So there's my secant line in blue. I have connected 2 points on the curve. Well, you could remember it like secant, like secret passage. It gets you around something without going through it, kind of like a secret passage. So you could think of secant line, secret passage. That's probably the best way to do it. Now, if we want to talk about a tangent line, let me erase that secant line here. Of course, let me redraw this curve, so just give me a minute, please. I want to draw it in black ink. Alright, I think that's good. So, a tangent line, on the other hand, touches a curve at one point, but it does not intersect the curve. I mean, it intersects technically since it touches, but it doesn't go through the curve. It only touches at one point. That's the tangent line in red. Well, tangent comes from the Latin word tangens, which means touching. So, tangens means touching, so that's how you can remember a tangent line. It only touches the curve at one point. The idea is that the tangent line, the slope of your tangent line is the slope of your curve at that given point. So, another idea is that, let's say I'm being asked here to find the slope in the equation of the tangent line at the point -1, -1, which is definitely on this curve. Well, what I can do is I can find a secant line. I could find the slope of a secant line in each direction from the curve, in each direction from my x value of -1, I can find a secant line, and then I can average the rates of those. I can average a slope of those two secant lines to get me a slope of a tangent line. That's what the idea of that is. So let's go ahead and dive into this. Now, in general, what you want to do when you're trying to use the average of two secant lines to find the slope of your tangent line is you want to, in each direction on either side of that point, you want to be equidistant apart in your x value. So let's say I'm going to find the slope of my secant line. I'm being asked to find the slope of this curve at the point -1, -1. Well, what if I start at x equals -2? It's exactly one x unit apart from -1. So let's pick -2. We know the slope, of course, is equal to y2 minus y1 over x2 minus x1. So that's going to be f of -2 minus f of -1 divided by that -2 minus 1 itself. Well, if I put in -2 for my x cubed, that would give me -8 minus that -1 to the third is minus -1 divided by -2 minus 1 is -3, which is going to give me -8 plus 1, which would give me -7 divided by -3, or 7/3. So the slope of my first secant line going from -2 to 1, and in fact, let me draw, man, if I could draw right, that would help, right? Let me draw my secant line from -2 to -1. So there's my secant line from x equals 2 to -1. That's a slope of 7/3. I'll draw the next secant line in red, just so we have a differentiation between the two. But if I'm going to average the slope of two secant lines to find the slope of my tangent line at x equals -1, I need to pick another x unit in the opposite direction. That's the exact same distance from x equals -1. Well, the exact same distance would be at x equals 0, wouldn't it? So let's go from -1 to 0. That'll connect 2 points on the curve. So there's that secant line in red. Well, what I need to do now to find the slope from -1 to 0, I'll take f of -1 minus f of 0, and I'll divide that by -1 minus 0, which would end up then giving me, let's see, that would give me -1 minus 0 divided by -1, or simply a slope of +1. So I now have the slope of both secant lines. If I want to find the slope of my tangent line to, and this is an approximation, if I want to find an approximation for my tangent line, what I need to do is take the slope of these two secant lines and take the average of them. So I have to take the average of the slopes of my two secant lines. So that's going to be 7/3 plus 1 divided by 2, which would end up giving me 10/3 divided by 2, which equals 10/3 times 1/2, which would turn into 5/3. So my approximate slope of the tangent line at x equals -1 is at the point -1 is approximately 5/3. Now here's the thing. Those were still relatively far apart. What if we took closer measurements? In other words, hypothetically, let's say we did -1.5 to -1, and then we did from -1 to -0.5. Because the closer you get on each side to that x value of -1, the more accurate the measurement of your slope is going to be when you average the slope of your two secant lines. So this is just one example. Now, I'll set this up here in just a second, but this time we're going to go with, so we got 5/3 before. Now, I'm going to redraw this curve. I might have to redraw a couple times, so patience please. Alright, so there's the curve. This time I'm going to go with -1.5, which would put me about right there. So f of -1.5 is about right there. To my f of -1. So there's my tangent line. So there's my tangent line right there from -1.5 to -1. And then I also want to do one from -1 to -0.5. So that's going to be about right there in the red. So let's take f of -1.5 minus f of -1 divided by -1.5 minus -1. Well, that's going to then give me what? What is -1.5 to the third power? Let's see what we get. I get about -3.375. And then minus f of -1. Well, f of -1 is -1, so this would actually be +1, divided by, now -1.5 minus -1, that's -1.5 plus 1, so that'd be divided by -0.5. So this would end up giving me -2.375 divided by -0.5. Well, what is 0.375 as a decimal? That actually turns out to be 3/8. So you would get -2 3/8. Well, the negatives are going to cancel out for sure. You get -2 3/8, which would be 19/8. So you'd have 19/8 divided by 1/2, which is going to equal 19/8 times 2/1, which would end up giving you a slope of 19/4. So using from -1.5 to -1 for your x values, you get a slope of 19/4. So let's go ahead. I'm just going to write that up here for the sake of room. You get a slope of 19/4. Now what if we went ahead and found the slope of the line from -1 to -0.5? So the second slope would be f of -1 minus f of -0.5 divided by -1 minus -0.5. Well, f of -1 is -1. Now, what is -0.5 to the third power? That's exactly what I need to get. Well, that would be -1/2, which is -1/8. So you would end up getting minus -1/8. That's actually +1/8. Divided by -1 minus -0.5. Well, that's -1 plus 1/2. So you're going to actually then end up with, see, -1 is -8/8, so that would give you -7/8 divided by -1/2. Well, your negatives are going to cancel out, so you would get 7/8 times 2 over 1, which would end up giving you 7/4. So the slope from -0.5 to -1 is 7/4. So we got the slope of the two secant lines. Now, what if we take, now what we want to do is find the slope of the tangent line, and we're going to average these two slopes in order to do that. So if I take the average of these two slopes, that would end up giving me 19/4 plus 7/4 divided by 2, which would give me 26/4 divided by 2. That's the same as 2 divided by 1. That would end up giving me 26 over 2. No, I'm sorry, wait a second. I multiplied wrong. Divided by 2, that's the same as 26 fourths times 1/2. That would give me 26/8, which would give me 13/4. Okay. So I had 5/3 before when I took the slope of the average of the secant lines. Now when I get closer and closer together, only half a unit apart, my slope is going to be 13/4. Well, we know 5/3 is that's 1 2/3. Now 13/4, that's 3 1/4. So the slopes have definitely changed. Now this time it's probably getting a little too close to graph, but let me graph this line here. Let's say I only go 0.1 units apart this time. I only want to go 0.1 units apart, okay? So let's say I pick, if I go to the left of x equals -1, that means I'm going to take f of -1.1 minus f of -1, divide that by -1.1 minus -1. Well, what is -1.1 to the third power? That's exactly what I need to figure out. I get -1.331, so -1.331. Now, f of -1 is -1. Negative of -1, that's +1. divided by negative 1.1 minus negative 1. Well, that's negative 1.1 plus 1. So this would turn into negative 0.331 divided by negative 0.1. Well, your negatives are going to cancel out for sure. You would end up getting a slope of 3.31, or that's 3 31/100ths, which actually, if we made this an improper fraction, that would end up giving you 331 over 100. So notice we're getting closer and closer to that x equals negative 1. That's on the left side of negative 1. Now let's go to the right. Let me write my slope up here of 331 over 100. Now let's find another secant line. Let's go just 1/10 of a unit to the right of x equals negative 1. So that would put you at negative 0.9. So if we take f of negative 1 minus f of negative 0.9, divide that by negative 1 minus negative 0.9, what you're going to get then is, well, f of negative 1 is negative 1 minus, well, what is negative 0.9 to the third power? Let's see what that is. You get negative 0.729, so this would turn into plus 0.279 divided by negative 1 minus negative 0.9. That actually turns into negative 1 plus 0.9. Well, this is then going to simplify into, let's see here, what is negative 1 so negative 1 plus 0.729, that's negative 0.271 divided by negative 0.1. Well, now your negatives are going to cancel out. This would become 2.71, which is the same as 2 71/100ths, or the exact same thing as 271 divided by 100. Now that we have those two secant lines, so the slope of the second secant line is 271 over 100. Now we can find the slope of the tangent line by averaging the slope of these two secant lines. So let's take the average of the slope of these two secant lines. So that's going to equal 331 over 100 plus 271 over 100, which is going to end up, let's see, all that divided by 2, I should say, excuse me. Alright, so let's figure out what 331 plus 271 is. That's 601. Wait, what? No, because I missed one. It's 602. Divided by 100. All that divided by 2, which would end up turning into 602 divided by 100 times 1 over 2, which would turn into 301 over 100. Are we starting to notice the slope is converging to a number? it's awfully close to 3, isn't it? This is literally 3 and 1/100th. Well, let's get really close. Let's get really close. Let's say we go 1,000th of a unit away. What if I did that? If I go 1,000th of a unit away from the from x equals -1, that's going to then give me f of -1.001 minus f of -1 divided by -1.001 minus -1. Well, now, what is -1.001 to the third power? It's not going to be a pretty number. -1.001 to the third power is -0.003300301. Then f of -1 is -1. Subtract -1, you're actually going to add 1. Divide that by -1.001 minus -1, that's plus 1. So this would simplify into -0.00300300301 divided by -0.001, which we know the negatives are going to cancel out. So that's going to end up giving you, when you simplify this, you would end up getting about 3.00301. That would be your slope of the first secant line from x equals -1.001 to x equals -1. So let me write that slope up here. So that slope would be 3.003001. Now, of course, we want to go the same distance apart the other way, to the right of to the right of -1. So that would end up being f. The second slope, the slope of the second secant line, would end up being f of -0.999 minus f of -1, all divided by -0.999 minus -1. Well, now, what the heck is -0.999 to the third power? Let's see what we get. So we got a doozy of a number here. We get -0.997002999. F of -1 is -1, so minus -1, that's plus 1. All that divided by -0.999 minus -1, that's plus 1. So this would simplify into 0.0299701 all over 0.001. Well, when we simplify this, divide by 1/1000th, that's the same as multiplying by 1,000, so this would turn into 2.997001. So now we got the slope of the secant line from -1 to -0.9. So let's see here. We have then that was 2.99. What did I say that was? $7,001. Now, of course, if we want to find the slope at x equals -1 at that point -1, -1, let's average these two secant lines together, the slope of the two secant lines. So that's going to equal then 3.003001 plus 2.997001, all that divided by 2. Now let's add all these up and divide by 2. You get 6.000002 divided by 2, which is approximately 3. And if we kept going, getting infinitely closer and closer and closer to that x value of -1, you would in fact come up with a slope of 3 at the point x equals -1. So we found sufficient evidence to say, because we've gotten so close, we can say the slope of the tangent line is 3. So the general slope of the tangent line is 3. Alright, so that's also the slope of the curve at the point -1, -1 is 3. So, how do we find the equation of the tangent line? Remember back from algebra, the equation of a line is y minus y sub 1 equals m times x minus x sub 1. So you got m being your slope, and then you have y minus the point, and then x minus the point. Well, if we plug in the -1, -1, and then our slope of 3 into the formula, this turns into y minus -1 equals 3 times x minus -1. So this would become y plus 1 equals 3 times x plus 1, which would give you y plus 1 equals 3x plus 3, which would then give you that y equals 3x plus 2. So we found the slope at the point -1, -1 to be 3 by averaging secant lines. And then that also means that slope at the curve at that point is the slope of the tangent line at that point. And we can use that slope to give us the equation of the tangent line. You get y equals 3x plus 2 at the point -1, -1. So here would actually then be the slope of your tangent line to the curve. There's your tangent line itself with the equation y equals 3x plus 2. Now, I'm just going to introduce it today, and then we'll actually work it out real quick. But the idea is, as I get infinitely closer and closer and closer and closer to that x equals -1, my secant line really starts to disappear, doesn't it? It actually starts to look more like a tangent line, and that's exactly what happens. To find it's also called the instantaneous rate of change. To find the instantaneous rate of change, it's going to be the limit as h approaches 0 of f of a plus h minus f of a divided by h. So basically that h, whatever x value you're given, whether it's -1, which we have here, or some other value of x, that h units means it's so infinitely close to it, you're pretty much at that point. This is your instantaneous velocity, your instantaneous rate of change, your instantaneous slope of the tangent line at that particular point. So what if I wanted to use this formula to find my slope at -1, -1? Why don't we use this formula? First, let me expand that -1 plus h. We'll say that a equals -1. That's our x value. So if I put in -1 plus h and I raise that to the third power, because we have to take f of a plus h, that is going to then equal, of course, -1 to the third plus 3 times that -1 squared times my h to the first power, plus then that would be 3 times -1 to the first times h to the second power plus my h to the third power. That's just from binomial theorem in algebra. So this is going to end up as the limit as h approaches 0. If I take my -1 for my a value, because that's where I'm taking my instantaneous rate of change at, so -1 plus h, and I raise that to the third, this will simplify into -1 plus 3h minus 3h squared plus h cubed minus that -1, because f of -1 is -1, all that divided by h. Well, we can simplify this here. -1 minus -1 turns into -1 plus 1, which is 0. And notice now with these, what's left in the numerator, you'll just have the limit here as h approaches 0 of 3h minus 3h squared plus h cubed divided by h. Well, notice you can divide both numerator and denominator by a common h, so this would end up equaling the limit as h approaches 0 of 3 minus 3h plus h squared. And wherever you see an h, put in 0 by direct substitution, because this equation that's left after you factor, 0 is defined everywhere in this equation. You literally end up getting 3. That would actually be the slope of your tangent line, the instantaneous slope at x at the point -1, -1. So when we average the secant lines, our estimate was spot on. We had a 3. It's exactly 3 at that point. So if you take the slope of enough secant lines, you can actually find, and you average them, you can get a very good estimate of what the slope on a curve is at a particular point. Alright, so let's do one more exercise. We won't do the instantaneous rate of change. I just wanted to show that to you what it looks like. Now, interesting enough, that formula I just showed you to find the instantaneous rate of change is basically the same formula for finding the derivative of a function. But let's change the function here. So we want to find the slope in the equation of the tangent line at the point 1, 0 for f of x equals the natural log of x. So we're going to graph the natural log of x. So we know at 1, 0, it crosses through. And then we know at 2, well, let's see what the ln of 2 is. I'd like to try to get as close as possible. So the ln of 2 is about 0.6931. So in fact, your curve does something like this, and then it goes down and rides along where x equals 0. You have a vertical asymptote at x equals 0, if we remember from algebra and pre-calculus. So here's your curve. We want to find the slope at this point 1, 0, which in turn will give us the equation of the tangent line. So here I'm going to draw a tangent line at 1, 0. That's the equation we want to find, which will also, finding the slope of that tangent line is the slope of this curve at the given point. So we definitely can't pick x equals 0 because the natural log is undefined when you have 0 inside of the argument of natural log. So we have to take greater than 0. Well, what if I start out with, what if I started out with 0.5? So what if I go to the left of x equals 1 by half a unit? That would put me at 0.5, so I'm going to find the slope of the first secant line from x equals 0.5 to x equals 1. So I'll take f of 1 minus f of 0.5, divide that by 1 minus 0.5. Well, f of 1, natural log of 1 is 0, minus, what's the natural log of 0.5? Let's do 4 decimal places. So that's about negative 0.6931. Divide all that by 1 minus 0.5, that's 0.5. So you're subtracting a negative in the numerator, you would end up getting 0.6931 divided by 0.5. Let's see what the approximate value is for the slope of your first tangent line. For your first secant line, excuse me. You get approximately 1.3862. That's just for the secant line from x equals 0.5 to x equals 1. Again, this is a decimal approximation, so that's just your first secant line. Now, in order to be able to average secant lines, we need to go in the other direction of x equals 1, that same amount of units. If we went half a unit to the right, that's actually going to put us at f of 1.5. That'll put us at 1.5 for x. So the slope of the second secant line would be f of 1.5 minus f of 1 divided by 1.5 minus 1. So what is the natural log of 1.5? Let's see what the heck that actually is. The natural log of 1.5 to 4 decimal places is about 0.4055. Now, minus f of 1, natural log of 1 is 0. Divide that by divide that by 1.5 minus 1, that's just divided by 0.5. Well, anything minus 0 is itself, so let's take that 0.5 0.4055 divided by 0.5, you get about 0.811. So now that we have the slope of both secant lines that are half a unit apart in each direction, let's average the slope of these two secant lines to find an approximate value for the slope of the tangent line. So if I take 1.3862 plus 0.811 and divide that by 2, I get approximately, let's see what we get here. (1.3862) plus 0.81 gives me about 2.1962. Divide that by 2, I get about 1.0981. So that would give me about 1.1. My slope of the tangent line, if I use the half unit apart secant lines and average the slopes, is about 1.1. Now, what if we got a little bit closer? I would like to get a little bit closer. Let's say I get 1/10 of a unit apart on each. So what if I want 1/10 of a unit away on each? So if I go 1/10 of a unit to the left of 1, that's going to give me 0.9 for x. So I'll find the slope of my first secant line is going to be f of 1 minus f of 0.9 divided by 1 minus 0.9. Well, we know f of 1 is in fact 0 minus what is the natural log of 0.9. Let's see what the heck that actually is. That's to 4 decimal places, it's about negative 0.1054. All that divided by 1 minus 0.9, well, that's going to be 0.1. So this would simplify then into 0.1054 divided by 0.1, which if we simplify further would be 1.054. So that's the slope of the first secant line from 0.9 to 1 for our x values. Now let's find the slope of the second secant line. If we go to the right 1/10 of a unit, that would put us at 1.1 for x. So to find the slope of the second secant line, we'll take f of 1.1 minus f of 1, divide that by 1.1 minus 1. Well, let's find what the natural log of 1.1 is. So let's see, the natural log of 1.1 is about 0.0953 minus the natural log of 1, which is 0. Divide that by 1.1 minus 1 is 0.1. Well, this is going to simplify into 0.953. For the slope of our second secant line. So we found the slope of the two secant lines around x equals 1. What about now if we average the two slopes? So let's average the two slopes to get a rough estimate of the slope of the curve at 1, 0, which will be the slope of our tangent line. So if I take 1.054 plus at 0.953, divide all that by 2. Let's see what I get here. You get about 2.007, divide that by 2, you get approximately 1. In fact, it doesn't matter how close I get to 1. Let's say I got on each side 1/100th of a unit away, 1,000th of a unit away, 1,000,000th of a unit away on either side of 1, and I average the slope of those two secant lines, I'm going to get a slope of 1. So the slope at the point 1, 0 is 1. We will actually end up getting a slope of 1 at the point 1, 0 for f of x equals natural log of x. So the slope is 1. Now we can use our formula to find the equation of the tangent line. Take y minus y sub 1, so that's y minus 0 equals 1 times the quantity of x minus 1. You just get y equals x minus 1. So the equation of the tangent line at the point 1, 0 for f of x equals natural log of x is y equals x minus 1. And of course, if you pick any other point on the curve, your slope is going to change, and therefore the equation of the tangent line will change. So that's how to find the slope of a curve at a given point using the average of secant lines. Now, in future tangent line problems, we'll know how to take derivatives, and we'll use limit formulas to be able to do a better job of this instead of having to find the average of secant lines. And then, of course, you use that slope you get to find the equation of the tangent line. So that's it for this lesson. Next lesson, we're going to do a couple of applied problems. For example, the rate of change of a hot water tank draining at a certain time, or a change in heartbeats per minute. We're going to do 2 applied problems that involve taking the average to get an instantaneous rate of change at a particular time. So I hope everybody has a great day. Take care.